Alright, in this video we're going to go over the notion of an antiderivative. Okay, so a few definitions and then we'll get into some problems. So what is an antiderivative? So we say a function, denoted often big f of x, is an antiderivative of a little f of x if the derivative of the big f of x equals the f of x, the smaller f of x. Okay, what the heck does this mean? Up to now, this entire course, we've been focusing on, give me a function, what's the derivative? Well, now we're going backwards. We're trying to set, now what we're saying is, if I already know the derivative, what's the original function that that derivative was derived from? Okay, and so that's what I have here written. That is, we are trying to find the original function that led to the derivative given by f of x. What's kind of cool about this is that we can actually check ourselves. We can check that big f of x is the correct antiderivative by taking its derivative. Because of this, the general form of an antiderivative is it's your big f of x plus some constant c. We'll get more into that in a little bit, but the quick of it is that basically when we take the derivative of a constant, it becomes 0. So what we're trying to find in this first section is we're actually trying to find all possible functions which have the derivative given by little f of x. The process of finding an antiderivative is called integration. All right. So when we take a derivative, we call that differentiation. When we find the antiderivative, it's called integration. The symbol we use to denote integration is the integral symbol, and it's going to be kind of that curly looking symbol there that I just highlighted. And so here is the kind of the form of the integration. You're going to be integrating f of x, and then you have your differential dx in your integral. Okay? If your function is a function of t, then you would have f of t dt. And all we're saying here is that when we integrate the function of x with respect to x, we get back the antiderivative, which is big f of x plus some constant c. All right. The above integral that we just went over is called an indefinite integral because it's true for all values of x within the domain. In a later video, we'll get into something called a definite integral where you restrict your values of x. All right. Super confusing, I know. Let's get through some examples together. All right, first example. They want us to verify that the antiderivative of f of x, which equals 8x, is big f of x equals 4x squared plus c. So as we mentioned, for this to be the correct antiderivative, what we're saying is that if we take the derivative of the big F and we get little f, then we say f of x is the antiderivative. All right. So basically, to verify that big f of x is the antiderivative, we need to take its derivative. So what is that? Let's see. So f prime of x, big f prime of x will be, well, the derivative of 4x squared is an 8x, and then plus c. Remember I told you that c represents any constant. So therefore, the derivative of any constant is 0. Therefore, f prime of x, which equals 8x, indicates that yes, big f of x is the antiderivative. Okay. Later on in the video, we'll get into how we actually calculate that function there. But yes, so big f of x is the antiderivative because its derivative equals little f of x. All right. Here's another one. Verify that the antiderivative of 3 over x plus 2 is equal to 3 times the natural log of x plus 2 plus c. All right. So once again, let's take the derivative of big F of x. Okay. Well, how do we take the derivative of a natural log? Well, first of all, we know that that constant 3 is coming along for the ride. It's a constant multiple. And then to take the derivative of the natural log of x plus 2, what we do is we take the derivative of the argument, the thing we're taking the log of. In this case, it's going to be, let's see, 1x plus 2, so that derivative is a 1. and then we put it over the original argument of x plus 2. And then just to make this look a little nicer, we can multiply the 3 into the 1 over x plus 2. And then that 3 is going to multiply just the 1. So we have 3 over x plus 2. All right. So since we just verified that the derivative of big F of x is equal to the given little f of x, then once again, yes, we can say that f of x, big F of x, which equals 3 times the natural log of x plus 2, is the correct antiderivative. So these two examples, I just wanted to show you what we're trying to do here. We're trying to come up, so in future questions, we're trying to come up with the big F of x that has a derivative that's already given to us. All right? And so how do we do that? We do that via what's called the power rule for antiderivatives. And what does the power rule for antiderivatives says? It says if I'm trying to integrate x to some power n dx, and that's your differential, and that tells you with respect to what variable you're working with, then it turns out that, remember, antiderivative, so it's the opposite process. The prefix anti means opposite. So I'm doing the opposite of the derivative. Instead of subtracting 1 from the power like we would for a derivative, we're going to add 1. And then instead of multiplying our derivative by the new power, we're going to divide our antiderivative by the new power. So the formula is you add 1 to your new power and then divide by the new power and then add on your constant c. Notice this is only true, or this is true for all n except for when n equals a negative 1. Why is that? You'll notice quickly if we plug in negative 1 into our formula, we're going to end up with a 0 in the denominator, which means the function is undefined. Towards the end, the last example that we'll do, I'll show you the case whenever n is equal to a negative 1. But for now, for the next couple examples, n will not equal a negative 1. Here we go. For example, suppose we're asked to take the integral of x to the 4th dx. That is, we're asked to find the antiderivative of x to the 4th dx. Right? Well, the integral of x to the 4th dx will be, all right, we add 1 to the power. Remember, we're going backwards. We're doing the opposite. So it becomes x to the 5th, and then we divide by whatever that new exponent is. In this case, it's 5. So it's x to the 5th divided by 5. And remember, we're trying to find all possible antiderivatives. So we're going to add a constant c at the end. Okay? Often what we'll do is, you see how that 5 is in our denominator? What we'll do is we'll rewrite this as a 1/5. X to the 5th plus c. So you'll see me write it like that going forward, but hopefully you understand where the 1/5 comes from. All right, that's the antiderivative. So essentially that's our big F of x. Really quickly, how do we know that that's the correct antiderivative? Well, let's take its derivative. For this to be correct, if we take the derivative of the antiderivative, we better get back to whatever is in our integral. We call that the integrand. All right. Well, if I take the derivative of 1/5 x to the 5th, what happens? 5 comes out, multiplies 1/5, leaves me with an understood 1. X to the 4th power when we take the derivative. And the derivative constant is c. All right. But the answer to the question is, what's the antiderivative? Is 1/5 x to the 5th plus c. Add 1 to the power, divide by the new power. Here we go. Integrate 5 dx. Okay. All right. Think of it like this. So we're going to still apply the power rule, right? So what I want to do is I want to rewrite this as 5 times x to the 0 power dx. Okay. Why is that legal? Because x to the 0 power is 1. 1 times 5 is 5. So I have not changed the actual integral yet. Okay. Now we can do the integration. Okay. And so when we integrate this, we're going to get 5 times x to the 1st power. Remember, we add 1 to the power, divide by 1, and then add c. Well, that just looks crazy. Instead, we can rewrite this just as 5x plus c. There we go. All right. Real quick, a word on the integral symbol. When do you drop it? When do you keep it hanging around? The integral symbol, Let me highlight it here. I'm talking about this right here. The integral symbol and dx, these are what we call operators, meaning after you perform the operation, you get rid of the symbol. For example, let's go back to a simple operator. Let's say we have the plus operator, 3 plus 2, right? Plus is an operator. After we perform the operation, we get rid of the symbol, right? So after we add and we get 5, notice we still don't have a plus operator hanging around. The same thing happens with integration. After I added 1 to the power and divided by the new power, aka after I did the integration, I drop the symbol because it's already been used up. So just keep that in mind when you're doing your work. All right, a few more examples. They want us to integrate the integral of 1 over the square root of x cubed. Okay, so let me just write this a little larger for us. Let's get a little break here. All right, so they want us to integrate 1 over the square root of x cubed dx. All right, well, the first step is I'm going to keep my integral symbol because right now I'm in the rewriting phase. Okay, so the square root of x cubed, we know from earlier this semester that that's going to be x to the 3/2 power. Okay, remember our rule is if we take the nth root of x to the m power, remember it's x to the m over n, dx. And then our next step is we are going to bring up that denominator, which changes the sign on that power, so we get x to the negative 3/2 power dx. Notice all of our steps so far, we have not actually performed integration. We're just rewriting the function. Now we are ready to integrate. How do we integrate? We add 1 to the power. So if we take x to the negative 3/2, add 1 to it, we get a negative 1/2. So take a negative 3/2 plus 1, you get a negative 1/2, divided by a negative 1/2 plus c. Okay? Now, the next step I want you guys to get in the habit of doing is remembering how do we divide fractions. Remember, we actually don't divide fractions. Remember, we multiply the fractions by the reciprocal of the denominator. So what I'm going to do is taking x to the negative 1/2 and dividing it by negative 1/2 is the same thing as multiplying the numerator by the reciprocal of the denominator. Right? Keep, change, flip, right? So I'm going to keep my numerator the same. I'm going to change my division to multiplication, and I'm going to flip, aka take the reciprocal of my denominator. So the reciprocal of a negative 1 over 2 is a negative 2 over 1, which I'm going to write just as a negative 2. And there we go, folks. That is our antiderivative. If you don't believe that's the correct answer, I want you to take a few minutes and check yourself by taking the derivative. Okay? And we should get precisely that value once we take the derivative of the antiderivative. Okay. All right. Sorry for the length of the video. I just want to make sure you guys are super comfortable with this material. All right, some quick properties. So I don't know if you guys recall, but we said there was a sum and difference rule for derivatives. And all that meant is that we can take each individual derivative. Well, we can do the same thing with integration. We can take each individual integral. In fact, what we can do is we can break this up into separate integrals. I'll show you an example in just a second. Then also similar to differentiation is we have the constant multiple rule. And what that means is that if I have a constant, okay, like a 5 or a 7, a negative 3.5, I can simply integrate my function and then have that constant multiple kind of hanging around. It's going to multiply my antiderivative. Okay? Let me show you a few examples here. For example, use the properties of integrals to express the following integral as simpler integrals. Can't talk. All right, so what they mean here is that they want us to apply the sum and difference rule and the constant rule to break this integral up, this single integral. We can break it up into 1, 2, 3, 4, 5 different integrals because of the sum and difference rule. So what does this look like? This will be the integral of 4x to the 5th dx. Just remember the integral sign and dx, they're hooked together. plus the integral of 3x to the fourth dx minus the integral of x squared dx plus the integral of 10x dx minus the integral of 7 dx. Okay? So as I said, we've broken this up into several integrals. And now what we're going to do is we're going to apply the constant rule, which says if you have a constant multiple, you can pull that outside of the integral. That's what it's really saying. So this equals, for the first integral, I can pull out that 4 because it's a constant multiple. So it's 4 times x to the 5th dx plus 3 times x to the 4th dx minus x squared dx, because there's no constant to pull out, plus 10 times the integral of x dx, and minus, and in your homework, they actually keep the 7 inside. If it's just a constant, they keep it in there. Okay, but if we wanted to, we could pull out the 7 and have a 1 dx there. But for your homework, they're going to have it written like that. Okay, so in your homework, if they ask you to calculate simpler integrals, this is what they're talking about. So this will be the correct answer choice if it's a multiple choice question. But I tell you what, let's actually go ahead and take this a step further. Let's actually go ahead and find out what this integral equals. Okay? So we're going to have 4 times, I'm going to do it like this, 4 times, and remember we add 1 to the power, divide by the new power. So it's going to be 4 times x to the 6th over 6. Okay? There is a plus c, but we'll talk about that in a second. Plus 3 times x to the 5th over 5 minus x to the 3rd over 3 plus 10 times x squared over 2 minus 7x. And then what happens is that each one of these integrals contributes a value c, right? Our arbitrary constant. Well, what we do is we collect all of those c's at the end and we just call it, you guessed it, c. So this c at the end is the contributions of all the constants in the integrals. Remember, c represents any constant. So a constant plus a constant plus a constant plus a constant is still a constant. All right. The next step we're going to do is we're going to simplify this answer here. All right. So coming over here, I have 4, which is being divided by 6 in my first answer, my first term. So I'm going to divide both sides, or excuse me, I'm going to simplify this by dividing through by 2. So we have a 2/3 x to the 6, or you can write it as 2x to the 6 divided by 3. That's fine. Plus 3 divided by 5 plus 3/5 x to the 5th minus a 1/3 x cubed plus, let's see, 2 goes into 2 one time. It goes into 10 5 times. So that'll be a 5x squared divided by 1, which is still 5x squared, minus 7x plus c. All right. So that is the antiderivative. But as I said, this particular question wanted us just to break it up. All right. Almost done, y'all. Really quickly, let's go through this one. So when they want you to find the integral of several terms, as we just saw, we can simply go piece by piece. So for this example, they want us to integrate 3, and what I'm going to go ahead and do is I'm going to go ahead and convert that square root of x to x to the 1/2 power, plus 5x minus 7. This is done with respect to x. And what I'm going to do is, as I said, the rule says basically just take each individual integral. So I'm just going to go ahead and do that separately, or excuse me, all at one time without breaking this up into 3 separate integrals. So when we integrate 3x to the 1/2 power, we're going to get 3, right? That's a constant multiple. It's coming along for the ride. Times x to the 3/2 power. How did I get that? It was 1/2 plus 1, which is 2/2. Okay? And I have to divide my function here by 3/2, my term by 3/2. Okay? Let me erase that there. Plus, what happens when we integrate 5x? We get a 5x to the 2nd power divided by 2 minus 7 times x to the 1st power divided by 1, which is just a 7x, plus our arbitrary constant c. Okay. Next thing is I'm going to, you see how this first term we're dividing by 3/2? I'm going to now switch that to multiplying by 2/3. So it's 2/3 times 3 x to the 3/2 power plus 5/2 x squared minus 7x plus c. And then 2/3 times 3, that reduces to just 2. So we get 2x to the 3/2 plus 5/2 x squared minus 7x plus c. All right. Once again, you can check yourself by taking the derivative of this, and we should get precisely what we have inside of our integral. All right, the very last question, I promise you, is what happens when the power is a -1? So I told you I would show you what happens there. So let me rewrite this for your convenience. Suppose we have the integral of 5 over x dx. Our first step, similar to derivatives, is that we have to rewrite this. So it becomes the integral of 5x to the -1 power. Okay. Notice, I'm going to come over here. Notice if you tried to integrate this with the power rule, we would get 5x to the 0 power, because we're adding 1, divided by that new power of 0, plus c, and this is just undefined. So that's why this has to have a separate rule. And that rule is the natural log. Why is that? A little bit of a side argument here. I don't know if you guys remember, but remember the derivative of the natural log of x was the derivative of x, which is 1 over x, which if I rewrite that, that's x to the -1. That's why whenever your power is a -1, it ends up being a natural log for that reason. Okay? So we're trying to find, remember what antiderivatives is. We already know we're dealing with the x to the -1. We're saying what function has the derivative that gives us an x to the -1? It's the natural log. For that reason, the integral of 5x to the -1 dx is 5 natural log of the absolute value of x plus c. And that's your answer. So why the absolute value? The absolute value is to ensure that the natural log is within its reasonable domain. If you remember from your college algebra class, you can't take the natural log of negative values. So this ensures that you're able to take the log of your answer. Okay. Like I said, I know there's a longer video, but hopefully that lays down the foundation for integration, and I'll see you guys in the next video.